Thank you very much for the nice introduction. And thank you for the invitation. It's a great city. I haven't explored much, but what I see so far, it's a very nice city. Okay, so my name is Didem Unat. I'm a faculty at Koç University. Before joining Koç, about 10 years ago, I did my PhD at University of California, San Diego, and then I worked 2.5 years at Lawrence Berkeley Lab. And then I was exposed to supercomputers a lot more when I was at Berkeley. So today I will talk about this different way of thinking how to program GPUs and talk about also some profiling tools that we develop in our group for multi-GPU programming. And as my title suggests, when CPUs take a back seat, so GPUs will be in the center, CPUs will be a little less important in my presentation. So this is, Jill set up a lot of good background for my talk, so I would like to thank him. So very brief history of Moore's law. Um, since 1965, we had doubling transistors every 2 years. We revised that every 3 years or so. But now, as some people say, maybe Moore's law is over. Maybe not. Okay, so a lot of things happen in those 50, 60 years, but I will focus on maybe the last 20 years because I'm not that old, maybe. Or what's relevant is for us is the last 20 years. So we started having first multi-core architectures around 2005. They were first introduced and then became common. And so we had a single core, and then we started having multiple cores in a chip. And programming, became a bit more difficult. So teaching multi-core programming became very essential and part of curriculum at the moment, undergraduate education. And um, while I was at Berkeley Lab, we were predicting that core count will double, every 2 years, similar to transistors, but it didn't happen. So we don't have thousands of cores in a chip, but we have, maybe tens or hundreds of cores. So the increase is a bit slower. Um, and then we started having not homogeneous, but heterogeneous architectures, right? We had multi-core, but then we started having these GPU accelerators attached, and then started programming not just we just learned multi-core programming, and now we had to learn, accelerator programming. And first GPU-based supercomputer ranked number one in 2010, and now a good percentage, maybe more than one over three, 1/3 of the supercomputers are equipped with GPUs. So now, definitely, um, this is inevitable ending, and we will have more and more GPU-based systems, right? And some people think that we will have actually different types of accelerators. Maybe, you can think of NIC becoming an accelerator because it computes, and then you need to now learn with Docker programming, maybe. So there are different accelerators now together acting as a processing unit. Okay. So, well, you mentioned a lot about data movement. Data movement is also a big part of our research. I started organizing this data locality abstractions, paddle workshops. The very first one we organized with Torsten in Lugano, Supercomputer Center, and then we had several workshops on paddle, and then we recognized data movement as a big part of the both performance and energy cost, and develop solutions how to think data movement as the first class of still in the programming rather than after having an afterthoughts of it. So what is data movement cost? So in order to add A and B, um, first you have these, let's say, in the memory. It can be cache or your DRAM or somewhere in the network. And then you need to bring these to the core, right? And then arithmetic logic unit is at the core. So you have to add these two numbers. And then all this process, you consume 100 picojoule if this is L2 cache. Okay, so but only 1 picojoule is actually spent in the arithmetic logic unit doing the addition operation, but the rest of the energy is consumed transferring the data in the control pad. So data pad and control pad consumes great amount of energy. So what we came, like, what do we say about this? Computation is very cheap. It's very cheap that we can actually afford to do redundant computation most of the time. So redundant means, you know, I calculated, but it's okay if I calculate it again because I can just forget my result and then redo it. It's cheap, very cheap. So data movement is the expensive part of the overall computation. So that's why, our focus is more on the data movement. And now this is when it's not even going through the network. So if you go off node, the numbers increase a lot more. So the cost increases. So this Tauber data locality is very important concept. So this figure seems complicated, but I will summarize it a bit. So this is the x-axis shows the years, and then the y-axis is the flops to words, like how many operations you're doing per bytes or 4 bytes that you bring into your CPU, and the gap is increasing. And then nowadays you can do hundred operations per word that you bring to the CPU. But our applications, they don't do that many operations. So this is called normally machine balance, but actually we should call it machine imbalance because machine can do a lot more operations, but applications don't need that many operations. They need the data movement much faster than what the machines can do, today's machines can do. So that's why there are a lot of effort now in the network, computing in the network, so that you don't have to move the data around. So this is basically causing a lot of machine imbalance issues. So leading to increase in the data movement speed and the computation speed. So another a similar conclusion from this is also there's also system imbalance. So I borrowed this slide from John McAlpin. We should have probably, this is for CPU, but we should plot it for GPU as well. So let me see, the red and purple shows latency, network and memory latency, and then orange and the green shows the bandwidth rates. So here again, higher number is not better. It's actually shows the imbalance, increasing imbalance between your compute speed versus your bandwidth speed or latency numbers. So, and the gap is increasing over time. Okay, so these are some backgrounds and trends, what we have in, what we care in HPC, how to address, how we should be addressing these trends. And today I will focus on two related projects that we do in my group. The first one is a new execution model for accelerators, in a way to address this latency coming from the network and data transfers and related to control paths and data paths. And the second is because data movement and communication plays an important role in performance, can we develop better tools to visualize and monitor the data movement activities among GPUs? So this is Frontier. It's number one system, 500. It's number one HPC system. There might be, companies may have bigger machines and flop rates, but this is located at Oak Ridge National Lab, and it has GPUs and CPUs um, in the system. So there's, and I will argue that um, it's a nice, machine, and it has several years of design. But I believe it could be designed differently. So I will argue that um, uh, they could save money and energy by not using, very strong CPUs in this design. So I'll come back to this idea later. Why is that? Because CPU is no longer is a central processing unit. So what CPU stands for is central processing unit, but CPU is not in the center of the world or universe anymore. Compute has moved to other devices. Switches can compute. We learn from Sharp. NIC is smart, so it can do some computation as well. And then some of the control still fits on the CPU. And I asked this question to Salvador whether it's essential. The parts that are still on the CPU, are they essential? Can we move some of these to the other devices, to the NIC or the GPU? So, and Jim mentioned in the morning that in his talk, CPU has become the advanced memory control, right? I think you said, maybe I should put in quotes. It's not really processing unit anymore, but it's a maybe advanced memory controller or helper to NIC. So its importance diminished over years, and that's the trend. But if you look at traditional GPU execution model, so you have the CPUs, and then you have an application code, and then you identify that regions of the code that should be accelerated, right? So I mark them as pink. So those are the things that you would offload to the GPUs, right? So in the traditional execution, so what CPU is responsible for is launching compute kernels, issuing communication calls, overlaps communication with computation, acts as a synchronizer, um, both within and across devices. And GPU is just responsible for computation, right? It performs the computation. But remember my few slides back, I said computation is cheap and data movement is the expensive part. And there's also control path involved on the CPU. So, I refer to this as CPU controlled execution. This is the offload model, but you can refer to it as CPU controlled execution. But what if we move most, uh, this control and data path to the GPU, and CPU just initiates the initial kernel launch, and the rest is handled on the GPU side. So GPU will be, performs the computation, issues the communication call, overlaps communication with computation, and also does the synchronization. And I refer to this as CPU-free execution. Okay. So, well, how do we implement this? Because this gives more autonomy to the GPUs. They can make decisions and then about their executions, and they have much wider control of their execution. And data path is easier to move because there's GPU initiated communication support now. But there's the other components that we leverage is persistent kernel. I'll explain in a second what that is. GPU initiated data movement, thread block specialization, and device side synchronization. So all of these components actually exist in CUDA programming. So we are combining them to create this execution model. So what is a persistent kernel? So You might be familiar with the discrete kernel. Discrete kernel is you launch the kernel finishes and returns back to the host, and then you launch another kernel and it returns back to the host when it completes. In a persistent kernel, you launch the kernel. Sometimes people refer to these as mega kernels or uber kernels. That you move the time loop and all the computation on the GPU side. So you launch the kernel once, and all the execution finishes, and it returns back to the CPU for when it completes. So this is a long-running persistent kernels grants the GPU more free, but it has limitations because of the corporate peppers. You can ask me about that later. And we rely on GPU-initiated inter-GPU communication, and we use enrichment heavily in this because enrichment has one-sided communication. It can do load stores directly to the other GPUs, and it has very efficient GPU side communication mechanisms. So it implements basically OpenShiMem, which is a PGAS model for GPUs. And this thread block spatialization we use for overlapping. So when you do when you implement a kernel, you launch a bunch of thread blocks. But what we do is we spare some of the thread blocks for communication, handling the communication, and some of them, majority of them for computation. This way, we overlap communication with computation on the device side. So and then CUDA cooperative groups API allows us to synchronize on the device side, within the device, and across devices. We use envision signal operation to synchronize between devices. So what does, as a concept, the CPU-free model is nice, but also it eliminates a lot of the overheads that come from CPU involvement in the execution. Okay, so such as kernel launch overheads, or communication calls, issuing the communication calls on the host side, or managing multiple streams, GPU events, and if you have the OpenMPI or MPI involved, there are barriers on the host side. So a CPU-free model can eliminate these or reduce these overheads with this the execution model. So here is some results showing this really reduces the overhead stemming from these operations. From 1 to 8 GPUs, our cost is almost flat, while CPU-controlled execution, this is for stencil, it increases. And especially strong scaling, CPU-free model helps a lot because when your domain gets smaller and smaller, the overhead, the cost of overhead, like the synchronization, etc., shows itself more, contributes more to the execution time. So as a use case, we had other use cases, but for this presentation, I picked a conjugate gradient solver, which has SAXP or AXP doing vector operations, and then SPMV, which is sparse matrix vector multiplication, and a dot product. And each step depends on the previous step. This is traditional or standard CG, what they call it in the literature. There's no overlap. So we implemented with this with CPU-free model, but also we implement the variant of this conjugate gradient solver if there's a pipeline CG in the literature. It introduces some auxiliary vectors so that it's possible to overlap communication and computation, and we can overlap the dot product global reduction with the SPME operation. So basically, we create this. All thread blocks will work on the dot product, local dot products, and then We will split the thread blocks into two groups, one doing the reduction of you know, the local dot products. It will do a reduction. And then other group of thread blocks will do the SPM, which is shown in blue here. And then they will do their part. This is where the overlapping happens, reduction operation with the SPM link. And then to do SAXPs, we again combine all the thread blocks to do this SAXP operation here. So all the thread blocks participate in the SAXP operation. Oh, I highlighted all of these, but I forgot about them. Anyway, so basically here, the overlapping happens, the thread block specialization. The first thread block does the local, combining the local scalars into one global scalar, and then the rest of the thread blocks are responsible for the SPM calculation. And then we do grid sync, and then do the SAXPs, and then multi-GPU grids. So the results show actually pretty nice improvements over this is 18 sparse matrices we tested, and 1.6 to 1.5 on average speed up over the CPU controlled execution, traditional CPU controlled execution for both pipeline and standard CG. So if I summarize the first part of my talk, so what we do is here, actually hard to scale part of computation, we try to remove the CPU from the critical path and then move those to GPUs and giving them more autonomy. And then there's less reliance on the CPU, and we are actually working with the DACE Talben group to automate, generate compiler. Actually, we submitted a paper, hopefully it will get accepted. So we auto-generate now CPU-free code using DACE on a multi-GPU, and then we added also enrichment support in DACE. And then we also have a runtime system that will handle the data movements and then splitting of work. We built that on CUDA graphs, so that's also will be published soon. So my question is, like, why do we need really expensive fat GPUs when we design a supercomputer? You know, you can have some modular design that's, you can have heterogeneous system where you have the GPUs, but they're attached to very weak, cheap CPUs just to do some networking or some running the operating system for it, to just launch the kernel from the CPU side. And then if you say that your applications, not all the applications use GPU, then you're wasting these nodes that contain GPUs. For those, you should have homogeneous system, which will have only multi-core, not GPUs attached to them. So this is my, I guess, recommendation, or you know, my observation about the current supercomputers built solely using GPUs, and then very heavy, expensive CPUs attached to them. So this way, you know, we can reduce the cost and energy consumption of the overall system. So if you would like to try out the CPU-free model, you can get it from our GitHub repository and let us know whether you like it or not, and maybe you can implement your own application using this execution model. Okay, so the second part of my talk is about Snoopy. Snoopy is a multi-GPU communication profiler and visualizer. So this is 2 weeks ago, we presented this in Japan, in Kyoto, at the ISC conference. This tool, we developed it out of need, because while developing CPU-free models and developing multi-GPU codes, we realized that support from NVIDIA's profiling tools, like some details that we needed, and decided to develop this tool. So this is the, showing the backside. There's lots of wiring and, communication happening. But when you use, let's say, inside systems for GPU-initiated communication or nickel calls, the top one is the nickel, very simple nickel calls, and then the bottom one is uh, if you if um, one of the arrays is located on a GPU, remote GPU connected with NVLink, and this is your local array. So GPU 0, let's say, accesses GPU 1's memory, grabbing data thanks to the one-sided communication, or NVMe or direct peer-to-peer loads and stores supports from CUDA. So, but if you look at inside systems, what it shows is this. Arguably not very useful for the programmer, because it just shows some bumps and activity um, in the NVLink, but it doesn't really help the end user, a programmer, about who was the target GPU, who was the source GPU, how much data moved, or uh, so how, like, which objects involved in this data movement, or where's the source code line, etc. So we, out of need, as I said, we needed more information about this, and we developed Snoopy. So Snoopy, most of the tools out there can monitor CUDA memcopy operations. Um, but their support for peer-to-peer direct access or communication libraries like Nickel and Enrichment is limited. And also, in terms of programmer point of view, we wanted to associate data movement with the objects or program objects, variables involved in that communication. So we wanted to link back to this information to the source code. That's why we have source code line attribution, but also data objects that are involved in that communication. So we implemented Snoopy. So Snoopy has 4 views at the moment. We have a lot of ideas to add more things, but one of the things is it can visualize the communication as a communication graph. So each node is a GPU, and then the link shows how much data in terms of transfers or bytes you can visualize either. And the node size and edge width represents the, whether they involve more or less communication. And then we can also represent the same data as a heat map with scales on the side. So you can also see as a metrics, communication metrics. So this is the system view. We have the object view. So these are the objects involved in communication. We don't list all the objects in the program because there might be too many. We just list the objects that are involved in communication. So you can, and then how much of the object is touched. But you can also select which GPU that you want to look at. And then if you go over the object, it will give more details about that object itself. And then not all the data is one-dimensional. So we added 2-dimensional view. If you enter the dimensions, it will visualize data in 2D, and then it will also highlight which part of the data is touched during communication. And then to again help the programmer, we added this code view, which will link the communication back to the source code. So it will show, for example, in line 88, this line contributes to 8% of the communication volume. And the other line 84, it contributes to 11% of the communication volume. And then it will show more information about that line on the side, like which GPU is involved in that communication, particular communication. Okay, so last view of the visualizer is the device view. In the device view, kind of summarizing the communication in terms of a single device point. You can imagine having, uh, one of the GPUs lagging behind, and you want to deep dive into that GPU, and then you can do that with this view, and it will show instructions involved in the communication because it's peer-to-peer direct. It will show its load or store. Okay, so I'll briefly talk about the implementation. You can look at our paper, how we implemented this, more details. So um, first, uh, we rely on binary instrumentation provided by NVBit. And so as a side note, NVBit is a kind of a research project developed some NVIDIA engineers at NVIDIA. But our internal communication, we found out that they don't support it anymore. So what we are doing at the moment is transitioning Snoopy to compute sanitizer, which kind of replaced, or at least there's it's supported and there's regular releases. But compute sanitizer also the binary instrumentation, so it works for our need. So we can monitor load store operations, API calls, like CUDA mallocs, etc., because that's needed for our object attribution feature. Okay, and on the GPU side, when the kernel is running, what we monitor is load store operations in addition to CUDA mem copy and nickel API calls and NVSHMEM calls. And then we do inspection, because in the load store operations, we need to differentiate what is local load store versus remote load store, because local load store is, I don't care, because it's not a communication. It's the data movement, but it's data movement to your local memory. But we care is the remote load stores, which happens to the other GPUs. Like we tested with 8 GPUs, but when we have access to Blackwell, we will test it with 72 GPUs. So it's really needed feature, because in 72 GPUs, when you access a remote GPU within the same node, it will filter those and then only monitor in the communication, visualize those remote accesses. So we do filtering, and then we implemented software sampling to reduce some of the overhead. But if NVIDIA provides address sampling natively, then we will be much better off in terms of overhead. We can reduce our overhead to 2-3x, but maybe, I don't know. And so we gather these in a message buffer, and then when the message buffer, reaches some threshold, we send it to the host for post processing. On the host side, we do this device attribution. So device attribution is like, I know this is a remote device access, but which device am I accessing? Like device 5 or GPU 5, GPU 7, etc. So we can do this thanks to UVA. And we identify the target GPU and the source GPU with this, and then log these information in a log file. But in addition to, because we instrument malloc, CUDA mallocs or other types of malloc operations, nickel uses a different malloc, let's say. We also, when an address is accessed, we can map that to the object, which object where this address is from, and then keep this as a, an object table where we count addresses or keep track of the addresses involved in communication. Okay. And in addition to those, we monitor nickel API calls. Um, I should say that it's not fully supported. We are doing our best, but there are things that we cannot capture in nickel. But I think it's also very highly needed feature, so we will improve our support. Enrichment, it's actually enrichment. So far we were doing single process executions, but enrichment uses multi-process. So each processing element is a process, so we can handle enrichment multi-process. Um, so I would say that we tested our tool in a node, but our next goal is to go off node and monitor multi nodes. And in the multi node, I think we will do a smooth transition because we already support multi-process cases. Am I doing with time? I'm not. Oh, okay. So so this this enrichment has very different memory mapping, but we can handle that. So in terms of evaluation, we looked at several use cases there in the paper, but I will mention a couple of them here. One of them is BFS. Actually, one of my students had a BFS implementation using a ring algorithm. Um, and then we realized that there's a link from GPU 1 to GPU 3, which shouldn't be there because it's a ring, right? So we realize our own mistake in our implementation by using Snoopy, and then with code line attribution, etc., we realize that we forgot to set the device when allocating one of the um, flag variable. So it really helped, and then we have now correct communication pattern, which doesn't have this link between those two GPUs. Um, and so another thing that we tested the BFS on another larger graph, and we realized that some of the communication buffer is hugely unused. So this is over allocation. It can be also used to see like we overestimated how much memory needed for communication buffer. So this is unused area. And if you're familiar with stencil, this nearest neighborhood communication, you can easily mess up with indices and then access wrong ghost cells or halo from your neighbor. So this illustrates that problem. Instead of accessing index 0, this is access index 1, which can be seen in the visualization of 2D objects. So we have some nickel tests as well. Um, here, no, already mentioned several times today. So there's more 8 GPUs, but 3 versus ring. It shows, different topologies of communication between GPUs as well. So we run all the nickel tests. So in short, as a summary, Snoopy is there to detect inter-GPU communication and data movement activities. We have a lot more ideas to integrate into Snoopy. What we are currently working on, a lot more than what is listed there, but multi-node support with, CUDA MPI. We have started on that and made good progress. Multi-node enrichment, multi-node nickel. And we also support Python, but object attribution and source code line attribution is not that easy in Python because it generates, there's levels of codes generates in between, and going back to the original source code line can be tricky. And since AI is hot, we have to have some AI components here. So we are adding an agent to help you understand the profile link data, whether, prompting like which GPU is the slowest or which node was lagging behind, or this kind of helper to the programmer with an agent that will run in the corner and then do some analysis for you. So those are in progress. And thank you very much.
Let's thank again our speaker.